Good afternoon, friends. Let us discuss the questions asked in 2022 Chemical Engineering, various subjects. As a whole, if you see, the paper trend was little different than the previous year examinations. The questions asked are quite conceptual and quite simple. Simple if the concepts are clear, moderate if you have just studied, and difficult if you have been little careless and you have not studied the subject as a whole. So let us start discussing the questions on thermodynamics and heat transfer. In statistical thermodynamics, the two questions are asked. Both are quite simple. One is extremely simple. It may not take more than a minute. Other question is conceptual, may take 2 to 3 minutes. Why I say the timing? Because in general, these questions we should be able to solve in 2 minutes. If any question is taking 5 minutes, that means in the true sense, the question may be little lengthy. So let us see the detailed procedure. Question number 37, classical thermodynamics. On PV diagram, one and condition 2, the properties pressure, volume and temperature are given. And then n moles of the ideal gas have been taken. And we are to find out the heat transfer from 1 to 2. There are two processes. I can say 1 to A and then A to 2. In 1 to A, heat transfer Q1A is given as work done plus change in internal energy. Then in the process A to 2, QA2 is given as WA2 plus U2 minus U1. What we are required to find out is Q12, which is Q1A plus QA2. This is U2 minus UA. This UA gets cancelled. Work done in process 1 to 2, constant volume process, is 0. So we are left with WA2 plus U2 minus U1. WA2 is P2 into V2 minus VA, and VA is same as V1 plus U2 minus U1. And what is U2 minus U1? Change in internal energy independent of the process, depends only upon the initial and final conditions, and that is Cv into T2 minus T1. Thus, if you see, the choice A is correct. So you can see how simple the question is. You have to just go through process 1 to 2. From the diagram you can see there are two processes, 1 to A and A to 2. Write down the first law of thermodynamics for the two processes, add together, it becomes from initial condition to final condition. Change in internal energy is always Cv into change in temperature. Work done in a constant pressure process, area under the diagram, that is pressure P2 and volume V2 minus VA, and VA is same as V1. Second question on thermodynamics. At 4 degrees centigrade, the coefficient of expansion beta, which is 1 upon V del V by del T at constant pressure, is given as 0. Coefficient of thermal expansivity minus 1 upon V del V by del T del V by del P at constant temperature is given as 5 into 10 raised power 4. And the molar volume V is given as 18 into 10 raised power minus 6. If S is the molar entropy at 4 degrees centigrade, we have to determine the term V del V upon del T del S upon del V at constant temperatures. This we have to determine. Now, P, S, V and the temperature T is constant. At two places, temperature T constant. So let us write down the equation with the temperature as constant. Out of the four terms, T, P, S, V, divide named as Tapasvi. So del P by del S at constant temperature, del S by del V at constant temperature into del V by del P at constant temperature, this is equal to 1. What I require is del S by del V at constant temperature. So this shall become, this term going on this side, del S by del P at constant temperature into del P by del V at constant temperature. This term required del S by del V is equal to these two terms. Let us check up what is del S by del P at constant temperature. By Maxwell relationship, here it should be del T P S V. We have moved horizontally, so it should be with negative sign. And further it is given that del V by del T at constant pressure is 0. When this term is 0, del S by del V at constant temperature becomes 0. And hence, V del S by del V at constant temperature becomes 0. So the answer for the required term becomes 0. If you know the art of writing down the equations, it becomes very simple. If you do not remember the Maxwell relationship, or you don't remember the identity, how do we write the four terms? Then it is the most difficult question. So these were the two questions asked in thermodynamics classical. Rest few questions were asked from the chemical thermodynamics, and that part will be discussed by another teacher who will be talking about the chemical thermodynamics. Now the question from heat transfer. Question number 30. There is a double pipe heat exchanger. Saturated steam is being condensed at a temperature of 100 degrees centigrade, and water enters at 75 degrees centigrade and exits at 95 degrees centigrade. The overall heat transfer coefficient is given as 1 kilowatt per meter square Kelvin, and the heat transfer area is 1 meter square. The specific heat of water is given as 4.2 kilojoule per kg Kelvin. We have to determine the mass flow rate of the cooling water. When one of the temperatures remain constant, whether it is a counter flow or a parallel flow, it does not matter. So we can determine the LMTD, which is delta T1 minus delta T2 upon log of delta T1 upon delta T2. This difference delta T1 happens to be 25 degrees centigrade, and delta T2 as 5 degrees centigrade. So 25 minus 5 upon log of 25 upon 5. Let us calculate this. It comes out to be 12.4267 degrees centigrade. Now we are circulating water around the steam. All the heat lost by the steam is gained by the cooling water. And cooling water MW CPW into delta TW. And this should be equal to UA into LMTD. MW we have to determine, which becomes UA LMTD upon CPW and delta TW. U value is 1 kilowatt, that means 1 into 10 to the power 3 watt, into area 1 meter square, into LMTD 12.4267 divided by CPW 4.2, it is in kilojoule, into 10 to the power 3, into delta TW, which is 95 minus 75. Zero 0.1479 kg per second. The answer given is 0.14 to 0.15. So this is okay. I hope this is the simplest type of the question asked from the heat exchangers. In the exam, data is available to you. You have to write this equation. And MW, you have to substitute the values where LMDD has already been determined. Next, question number 40. There is a long copper wire of diameter 1 mm. Surface temperature is Ts. Surrounding temperature is Ta. Let L be the length and the convective heat transfer coefficient H is given as 20 watt per meter square Kelvin. This is quoted with 2 millimeter thick insulating material. Ts and Ta remain unchanged. By providing insulation, heat loss is to be reduced. Maximum allowable thermal conductivity is to be calculated. When there is no insulation, Q without insulation is given by Ts minus Ta upon the resistance, which is 1 upon Ha, and A is 2 pi Ri into L. And when insulation is provided, then the heat transfer is Ts minus Ta upon 1 upon K 2 pi L log of Ro upon Ri plus 1 upon H 2 pi Ro into L. Now Q without insulation upon Q with insulation, this divided by this. This Ts minus Ta gets cancelled. This term shall go in the numerator. 1 upon K 2 pi L log of Ro upon Ri plus 1 upon H 2 pi Ro into L divided by 1 upon H 2 pi Ri into L. If you cancel the term 2 pi L, 2 pi L and 2 pi L. Without insulation, heat transfer is more. With insulation, heat transfer is less. That means this has to be greater than or equal to 1. That means 1 upon k maximum log Rho upon Ri plus 1 upon H Rho equal to 1 upon H Ri. So 1 upon k maximum log of Rho 2 millimeter and 0.5 millimeter. 2.5 millimeter upon Ri 0.5 millimeter. This should be equal to 1 upon H into 1 upon Ri minus 1 upon R. Thus, K maximum is equal to log of 5 upon 1 upon H into 1 upon Ri minus 1 upon R. If you calculate, let us do step by step. Log 5 upon 1 upon H, and H is 20, into 1 upon Ri 0.5 minus 1 upon Ro 2.5. It is 20.1179 watt per millimeter Kelvin. Divide by 1000 shall become watt per meter Kelvin. And this should come out to be 0.02 watt per meter Kelvin. A number of options are available. 0.02 is the option A. So A is correct. Any point which is not clear? Quite simple. The first chapter that we discussed, we have to write down the heat transfer with and without insulation. And then without insulation, heat transfer is more. With insulation, heat transfer will be reduced. So this term comes out to be greater than 1, and for maximum thermal conductivity it should become equal to 1. So equate the two, substitute the values and get the answer. Next question is question number 41. There are two planes parallel with temperature 1000 Kelvin and 500 Kelvin. A radiation shield is to be installed in between the two. Emissivity of the walls and sheet are same. Melting temperature of shield is 900 Kelvin. We have to determine the maximum number of shields which can be installed. If Tr is the temperature of the shield, and this should be less than 900 Kelvin. If you see the answers, they are given as 0, 1, 2, 3. That means we have to try which number of shields, the temperature of the shield should be less than 900. Sigma A into T14 minus T24 upon 2 upon emissivity minus 1. If one shield is provided, this shall become half of the total. That means sigma A into T1 minus Tr upon 2 upon epsilon minus 1. This will mean T14 minus T24 upon 2 is T14 minus Tr4. T1 1000 raised power 4, T2 500 raised power 4 upon 2 is 1000 raised power 4 minus Tr raised power 4. And we have to determine the temperature Tr. It comes out to be 853.7 Kelvin, which is lower than 900 Kelvin. If two shields are used, then sigma A T14 minus T24 upon 4 into 2 upon epsilon minus 1. This should be sigma A into T14 minus TR4 upon 2 upon epsilon minus 1. Temperature should be reduced 4 times. That means T14 minus T24 upon 4 is equal to T14 minus TR4. And let us calculate the value of TR. This comes out to be 935.4 Kelvin. So this way, if we keep on increasing the number of shields, the temperature of the shield shall keep on increasing. This is more than 900 Kelvin. Therefore, two shields cannot be used. And hence only one shield should be used. Thus, our option A is correct. So in this question, what you should know basically, that heat transfer will be getting reduced by half when one shield is being used. When two shields are being used, this will become 1 by 4. And rest you have to substitute the values and get the answer. Next is question number 42. On a vertical plate, steam is being condensed. X is the vertical distance. From the top edge of the plate, and the local heat transfer coefficient local heat transfer coefficient Hx is proportional to mass flow rate at x raised power minus 1 by 3. The ratio of the average heat transfer coefficient H average to the heat transfer coefficient at the bottom of the plate, where x is equal to L. This ratio is to be determined. Now, in this question, if you remember the final result of average heat transfer coefficient, the question belongs to only two lines. If you don't remember, you cannot start the question. H average we had derived in the class 0.943 into rho L into rho L minus rho V into G into K cube into lambda upon mu L Tg minus Tw raised to the power 1 by 4. And if we talk of local, it is rho L into rho L minus rho V into G into K cube into lambda upon mu x into Tg minus Tw 4 raised to the power 1 by 4. What we have to determine is the ratio of H average upon H local when X is equal to L at the bottom of the plate. And this becomes 0.943 into rho L into rho L minus rho V into G into K cube lambda upon 4 mu L Tg minus Tw raised to the power 1 by 4. And here it is mu L Tg minus Td. And this is rho L into rho L minus rho V into G into K cube into lambda upon 4 mu L Tg minus Tw raised to the power 1 by 4. 0.943 within bracket all the things cancelled except for denominator 4 raised power 1 by 4. This will go in the numerator and shall become 4 raised power 1 by 4. This comes out to be 1.333. And if you see the answer, one of the answers is 4 by 3. And this is option number B. So if you remember this, there are two equations to be written. Simplify and get the result. And this heat transfer coefficient is proportional to the mass flow rate, which is given as mass flow rate power minus 1 by 3. This mass flow rate doesn't come into the picture. Heat transfer coefficient we have to determine. Next is question number 54. A cylindrical fin is given whose diameter is given as 24 millimeter. Heat transfer rate from the fin is given as 60% of the heat transfer rate when the entire fin is at the wall temperature. Further, it is given that the effectiveness of the fin is 10. We have to determine the length. Heat transfer from the fin is given by under root of HPKA into Ts minus T infinity into tan hyperbolic ml. This is equal to 0.6 of heat transfer if the entire fin was at the wall temperature. That means H A is P into L into temperature difference Ts minus T infinity. So Ts minus T infinity gets cancelled. From here, I can get the value of tan hyperbolic ml, which is 0.6 HPL upon under root of HPKA. The effectiveness of the fin, which if you remember is under root of PK upon HA into tan hyperbolic ml. If I substitute the value of tan hyperbolic ml, it is under root of Pk upon Ha into 0.6 HPL upon under root of HPKA. And this effectiveness is given to be 10. This Pk and Pk gets cancelled. It becomes 0.6 HPL upon under root of HA. Root cancel, it becomes H. We have to determine L. L is equal to 10 A. A was the area at the base of the fin. L is equal to 10 A. A is pi by 4 d square upon P. P is pi into d. So pi gets cancelled, d gets cancelled, and it becomes 2.5 into d. 2.5 and diameter was 24 millimeter. L is equal to 10 and this 0.6 shall come here. Then upon 2.4 and 224, which comes out to be 100 millimeter. Now this case was applicable when this end of the fin is insulated. To account, nothing is given. To account for heat transfer from the edge of the fin, from the tip of the fin, L should be equal to L minus d by L is 100 millimeter, D is 24 millimeter upon 4, 6, 100 minus 6, 94 millimeter. Thus, the answer given is 94. Most of the students may write this, but those who have done some problems on the design of the parameters for the fin, they must have noticed that this equation was when the tip of the fin is insulated. This is not given in the question. That means some heat transfer may take place from here also. And for that, in most of the books, the relationship given is actual length should be length minus d by 4. So 100 minus 6, 94 millimeter. Next question, question number 55. There is a single effect evaporator. The concentrated liquid comes out from the bottom. The feed is given, which is 10,000 kg per hour at 40 degrees centigrade. the saturated steam is supplied, which is 7500 kg per hour at the temperature of 150 degrees centigrade. The boiling temperature of the solution in the evaporator is 80 degrees centigrade. The average specific heat of the solution Cp is 0.8 kilocalorie per kg Kelvin, and the latent heat of vaporization is given as 500 kilocalorie per kg. Then some steam is being used and some steam goes out as vapor. The overall heat transfer coefficient U is to be determined. And further, the steam economy is given as 0.8. Now this 0.8 is the volume of the steam produced divided by the volume of the steam supplied. So from here we get the value of V set to 500 into 0.8. That means 6000 kg per hour. Now how much heat is supplied? This is U A into saturation temperature minus that of the feed. Which must be equal to the volume of the steam produced into its latent heat plus the heat which is supplied to the feed, which is F into Cp into T boiling minus T feed. U is to be determined. V we have calculated 6000 into the latent heat 500 plus the feed which is 10,000 into Cp is 0.8 into the boiling temperature which is 80 minus the feed temperature which is 40 divided by Ts, the temperature of the steam supplied, that is 150, and how much is the temperature boiling? That is 80 into area, and area is given as 70 meters square. Simple one equation. Conceptually you should be alright, and then substituting the values, 677.55 kilocalories per meter square, temperature difference in Kelvin or in Celsius. The answer given is between 675 and 680. So our result is okay. Thus, friends, we have solved all the problems on the heat transfer, which some students responded that the questions were little difficult, but you must have seen solutions being so simple, only the presence of mind is required. So you can check up whether you could attempt from thermodynamics and heat transfer all questions properly, or you have committed some simple mistake, or you couldn't attempt altogether. Anyhow, I wish to all of you best of luck in the examination. Thank you.